In the last lecture, we find cumulative distribution function of a random variable, and then we have seen some of the examples. In this lecture, we are going to discuss some important properties of cumulative distribution function. So just to recall that, if you remember that we defined cumulative distribution function as a function, so CDF we have defined as fx at the point small x is equals to probability that x is less than equals to x for all x belongs to R. Okay, that's why we have defined. So now we are going to see some of the properties of the cumulative distribution functions. We are going to see these main 5 properties. So the first property says that cumulative distribution function is non-decreasing. So it is either increasing or it may remain constant. Okay. Then this second property tells that distribution function as x tends to infinity will be 1. Distribution function as x tends to minus infinity will be 0. The fourth property tells that limit h drops to 0, f of x at the point x plus h equals to f of x at the point x. That means that cumulative distribution function is right continuous. And then the fifth point says that cumulative distribution function may not be left continuous, it can have jump. And note that as we have that cumulative distribution function is a monotone function, non-decreasing function, that means whenever we have a jump, it will be a jump discontinuity. Okay, whenever we have that discontinuity, then that means it will have a jump discontinuity only. Not only that, in your real analysis course, you must have seen this result that for a monotone function, there could be only countable number of discontinuities. So being the cumulative distribution function being a non-decreasing function, that means a monotone function, the number of discontinuities of the cumulative distribution function will be countable. So let us now try to prove this theorem along with the intuitive meaning of the theorem. The intuitive meaning of these different properties, let us try to see. Okay, so the first theorem we are going to prove is that the first thing, the theorem 2.1, theorem 2.1, the first thing we are going to prove is that the first part we are going to prove that to show distribution function is non-decreasing. So what does this mean? What we need to show? So that means we need to show that for any x1 less than x2, f of x at the point x1 less than or equals to f of x at the point x2. Okay, to show that the cumulative distribution function is non-decreasing, we basically need to show that distribution function at the point x1 is less than equals to cumulative distribution function at the point x2, where x1 is less than x2. Okay, so the proof of this one is quite simple. It is direct consequence of the definition. You see that the distribution function at the point x1, which is basically by definition probability that x is less than equals to x1, and distribution function at the point x2 is nothing but probability that x is less than equals to x2. And notice that I have x1 here, I have x2 here. So that basically means that this is basically the probability that the random variable is in this part, and this is the probability that the random variable is in this part. Now, as minus infinity to x1 is a subset of minus infinity to x2, So that basically implies that probability x belongs to minus infinity to x1 will be less than or equals to probability that x belongs to minus infinity to x2, and that completes the proof. And that completes the proof because this is exactly the distribution function at the point x1, and this quantity is the distribution function at the point x2. So that actually proved. Okay, clear? So the non-decreasing, the distribution function is non-decreasing. That is the basically consequence of the fact that probability the distribution function is probability x is less than equals to x, and then minus infinity to x1 is a subset of minus infinity to x2 if x1 less than x2, and then probability of a smaller set is less than equals to the probability of a bigger set. Using that thing, we can write that the distribution function at the point x1 is less than equals to distribution function at the point x2. The next point we need to show limit x tends to infinity, f of x at the point x is equals to 1. See, intuitively this is quite meaningful in the sense that note that probability that distribution function is basically probability that x is less than equals to x. Now if I take x goes to infinity, that means this point I am pushing further this side, and when x is increases and increases to infinity, that means I am covering the whole real line, and x belongs to real line. That probability is 1 because x is a random variable, and the definition of the random variable is that x is a function from s to r, so x belongs to r. That probability is always 1. Okay, so intuitively that makes sense. Now mathematically we are going to prove this, and prove it basically the idea I told you that needs to be written in mathematical form. That's all. So let xn be a sequence, be an increasing sequence such that xn tends to infinity as n tends to infinity. So xn is a sequence of real number. It is increasing and it increases to infinity. Now define an equals to the set collection of omega belongs to S such that x omega is less than equals to xn for all n equals to 1, 2, and so on. So an is basically the set where x is less than equals to xn. Now as xn is an increasing sequence of sets, so that means as xn increasing that means the sequence of events EAN is also increasing. And it is very easy to show because if you take omega belongs to AN, that implies that x of omega is less than or equals to xn, which is again less than or equals to xn plus 1 because xn is an increasing sequence of sets, and that implies that x omega is less than equals to n plus 1, and that implies that omega belongs to an plus 1. Okay, so as xn is increasing, the sequence of event an is also increasing. So that means if I talk about the limit of probability of an, then I take the limit inside the probability. So now you notice that, so using the continuity of probability, the limit n tends to infinity, probability of an is equals to probability of limit an as n tends to infinity. Now, what is probability of an? Probability of an is basically nothing but probability that x is less than equals to xn, and which is nothing but the distribution function of x at the point xn. What is limit an? The limit an, n goes to infinity, being an being increasing sequence, it is the union of an, and that is basically the whole sample space. And you can check it very easily. Suppose how can we check that? Well, let omega belongs to s. We need to show that omega also belongs to the union of a. That means omega belongs to an for at least one n. So omega belongs to n. So that means that x omega is a real number. Now, if x omega is real number, so that means that x omega is less than or equals to xn for some n. Why this is true? This is true because an increases to infinity. Now, if there do not exist any n such that x omega is less than xn, that means x omega is infinity. But that is not possible because x omega belongs to R. Okay, so that actually shows that omega, that actually shows that omega belongs to a n, and implies that omega belongs to union of a n. Similarly, now if I assume omega belongs to union of a n, that implies that omega belongs to a n for some n greater than equals to 1. So that means x omega is less than equals to xn for some n greater than equals to 1. So that means this or actually the other way thing is obvious that because of the definition of an, because the definition an by default is the subset of a. So if omega belongs to s, if omega belongs to an, then that has to belongs to a. So that is a consequence of the definition of a, and I do not need to go like this. So that means that union of n, which is limit of n equals to a. So what I get? So I get that limit n tends to infinity f of x at the point xn is same as limit n tends to infinity probability of an, which is same as probability of limit n tends to infinity an, which is same as probability of the sample space, and which is by the definition of the probability 1. So that proves the property. Okay, so the idea here basically, well, intuitive idea here that when x is pushed to infinity, that means I am covering the whole real line, and that's why the this limit should be 1, and the mathematical proof is through the continuity of probability. We need to create a increasing sequence of events, and the increasing sequence of events should cover the whole sample space. That is basically the idea. Okay, I hope this proof is clear. The next property says, this property I will not prove because proof is almost the same as before, just I give you the hint and I stop there. The next property says that limit x goes to minus infinity f of x at the point x equals to 0. Again, intuitively it makes sense because the distribution function is basically probability in this side. Now, if I push this x to negative infinity, that means that no point will remain there. So probability will be 0. So probability, it look like probability of 5. So probability will be 0. And the proof goes exactly like this way. So we need to consider decreasing sequence xn such that xn goes to negative infinity as n goes to infinity. Now you can define Bn, which is basically omega, such that x omega is less than equals to xn. Then this n are decreasing sequence of sets. So now define Bn equals to omega belongs to S such that x omega is less than equals to xn, show that this is a decreasing sequence of events, and also so that limit Bn n goes to infinity is equals to phi, the null set, and then just proceed like before and you have the result. So complete it. Complete it. The next property, fourth property, says that cumulative distribution function is right continuous. So what does this mean? This basically means that, which is equivalently mean that limit h drops to 0, f of x at the point x plus h is same as f of x at the point x for all x belongs to the real line. Okay, and why this is true? Again, the proof is as before. So consider a decreasing sequence xn such that xn goes to 0 as n goes to infinity. So note that as this is a decreasing sequence of sets, the decreasing sequence of real numbers, and xn goes to 0, that means all the xn's are on the positive side of the real line. Okay, or maybe 0. And now we will again go as follow as above, that we define Cn is equals to collection of omega belongs to S such that x omega is less than or equals to x plus xn. Then clearly probability of Cn is basically distribution function at the point x plus xn, and and also we have that Cn n greater than equals to 1 is a decreasing sequence of events. Okay, now it is easy to see that limit Cn n tends to infinity is nothing but the set omega belongs to S, such that x omega is less than or equals to x. It is easy to show this one. So complete this one, take this one, complete this one, and take this one and complete this one. So now we have that, well, limit n tends to infinity, f of x at the point x plus xn is equals to limit n tends to infinity probability of Cn, which is same as probability of limit Cn, which is same as the distribution function at the point x. So that completes the proof. That distribution function is a right continuous function. The next property, property 5, tells that, well, the limit h drops to 0, f of x at the point x minus h is same as distribution function at the point x minus probability that x equals to x for all x belongs to R. So note that this property says that if this quantity, that probability capital X equals to small x, is equals to 0, then the distribution function is left continuous at the point small x. Previously, we have proved that the distribution function is right continuous. Now, if the distribution function is left continuous, that means distribution function is continuous at the point x. So, if probability x equals to x is 0, then the distribution function is continuous at the point x. If probability x equals to x is strictly greater than 0, the distribution function is discontinuous at the point small x. Okay, let us try to prove. The proof again in the similar fashion as before. So let xn be an increasing, or I should take increasing or decreasing, anything is fine. I should take increasing sequence such that xn goes to 0 as n goes to infinity. Note that I take xn is increasing sequence, that means increasing sequence, and xn goes to 0, that means each xn is less than equals to 0 for all n. Xn's are non-positive. Xn's are non-positive, that means this x minus h, this point is equivalent to x plus xn. Okay, so that's why we define dn, which is equals to um, omega belongs to s, such that x omega is less than or equals to x plus xn. What kind of set dn is? So dn n greater than equals to 0, greater than equals to 1 is what kind of set this is? If x increases, xn increases, that means this point is going towards x from the left hand side. So this is a again increasing sequence of events. So if dn increases, so then dn is increasing, so that means limit n tends to infinity, dn is union dn n equals to 1 to infinity. And note that this set is equals to omega belongs to s, such that x omega is strictly less than x. Note that this equality sign is not there. Why equality sign is not there? Very easy to see that. See, I have x omega is less than equals to x plus xn. So that means that I will never attain the point x. Okay, I'll never attain the point x. And note that here increasing, basically I mean it is strictly increasing. Okay, here increasing, I basically mean it is strictly increasing. And so that means I cannot attain the point x. So basically the idea is nothing but, well, I have x here, the xn actually approaches to 0, so x plus xn approaches to x, but it will never reach the point x. So that's why I have strict decreasing side here, and that is the reason I have this quantity here. I will have this quantity here. So now I can write limit n tends to infinity, f of x at the point xn is, at the point x plus xn, at the point x plus xn is equals to limit n tends to infinity, probability of dn is equals to probability of limit n tends to infinity dn, now which is increasing. So that means that this is probability that x is strictly less than x, and x is strictly less than x, that can be written as probability x is less than equals to x minus probability that x equals to x, which is same as a distribution function at the point x minus probability that x is less than x is equals to x. Okay, so that shows some five properties of cumulative distribution function. So it's proved. Five property of cumulative distribution function. Please cross check this one, that understand this one. Here I will have strict inequalities. Yeah, try to understand. If you have any doubt during the doubt clearing session, please ask me. Well, So we have shown that this five property of cumulative distribution function. The next theorem is basically kind of a converse, and it says that if I have a function g from R to R which satisfies the properties 1 to 4 above, then g will be cumulative distribution function of a random variable. So again, if you go back to the theorem 2.1, it says that, well, if I have a cumulative distribution function, then it satisfies property 1, 2, 3, and 4. And the theorem 2.2 says that if any function satisfies condition 1, 2, 3, and 4, then it will be a cumulative distribution function. So these four properties, the first four properties, are kind of a if and only if properties for the cumulative distribution function. And clearly that means if I am given with some function, I can check if the function satisfies all these four conditions or not. If it satisfies all these four conditions, then that function is a cumulative distribution function. If it do not satisfy at least one condition among the first four conditions, then it will not be a cumulative distribution function. The proof of this theorem, that the theorem 2.2, is not possible to do in this course, but as you understood that this theorem is an important theorem to check if a given function is a cumulative distribution function or not. Okay, let us put some remarks here. Note that when we define the random variable, there is no involvement of probability. Random variable is merely a function from the sample space to R. So there is no probability attached to this one. On the other hand, when we are talking about cumulative distribution function, the probability comes into the picture, because the definition of the cumulative distribution function is probability that x is less than equals to x. So that means that if I change the probability on the sigma field over S, and if I keep the definition of the random variable same, the cumulative distribution function may change. Okay, so that is point out here that note that a random variable is just a function defined on the sample space and does not depend on the probability. However, the distribution of the random variable, by the distribution we mean that cumulative distribution function. That is one way of saying the distribution. The cumulative distribution function depends on the probability. Hence, keeping the function same, that means random variable same, if we change the probability, then the random variable will remain same, but the distribution function, that means the distribution, may change. And you can check it very easily with the coin tossing problem that I toss coin twice. And in the example 2.1, we have taken that all the elementary events are equally likely. That means probability of head-head equals to probability of tail-tail equals to probability of head-tail equals to probability of tail-head equals to 1 by 4. Now, if I change this one to this thing, something else, which is maybe if we take probability of head-head is 9 by 16, tail-tail is 1 by 16, head-tail and tail-head are same equals to 3 by 16, then you can show that in the similar way you can show that the distribution function of x become this one, which is different from the cumulative distribution function which we have got in the example 2.1. So keep this thing in mind that, well, the random variable is a function defined on S to R. So if I change the probability, the random variable may not change if I do not change the definition of the random variable. But if we keep the definition of the random variable same, but if I change the probability, then the cumulative distribution function, or in general the distribution of the random variable, may change. Okay, so there is a simple definition. What is atom? The atom means that if probability of x equals to x is greater than 0, then the small x is called the atom of the cumulative distribution function of x. or sometimes it is called the atom of the random variable x. And if you understood that, or you have already discussed that, if because of the consequence of the fifth property, if x is the atom, then the cumulative distribution function is discontinuous at the point x. If x not a atom, then the cumulative distribution function is continuous at the point x. Okay, so now another important thing regarding the distribution function is nothing but that you see that different kind of probabilities regarding the random variable, that random variable belongs to some interval. This kind of probabilities can be written in terms of the distribution function. Obviously these things are limits, so this minus means left limit and plus means right limit. So obviously there will involve limit, but we will be able to write in terms of the distribution function or limit of the distribution function. Okay, how we can do that? Let us just see it from here. That probability of x less than equals to x, by definition this is the distribution function. So if I know the distribution function of a random variable, I can able to find out what is the probability that x is less than equals to a for some particular value of small a. Okay. On the other hand, if I try to find out what is the probability of x is strictly less than a, that I can find by taking the limit x increases to x of the distribution function. So that means again, if I know the distribution function, I can able to find out what is the probability that x is strictly less than a. Clear? Again, how can you prove that? This proof is basically subproduct of the proof of equation of property 5 of theorem 2.1. You can just take it. I am not going into that proof. Rather, I am going to give you the intuitive ideas here. Okay, so now first thing we have already discussed is that, well, if I have to find out probability x is less than equals to a, if I know the distribution function, I can find it out directly. Next point is that if I try to find out x is strictly less than a, claim is that it is basically limit x increases to a of f of x at the point f of x, which is basically nothing but left hand limit at the point a. And what is the intuitive idea? Intuitive idea is very simple. So what I want that I will reach as close as possible to the point a. Sorry, this is not x, but this is a. So I will reach at as close as the point a, but not the point a is included. So that means I have to take the limit from this side, and this is the left limit. Okay, then I can write probability of a is less than x is less than equals to b. Note that this quantity can be written as x is less than equals to b minus probability that x is less than equals to a. Why this is true? Again, so I try to find out what is the probability of x in the interval a to b. And this interval you can write nothing but all the points below b, including b, so the interval minus infinity to b close, and then I need to subtract the interval minus infinity to a close. So that means I can write this probability x lies between a to b, where a is open and b side is closed, as probability x is less than equals to b minus probability that x is less than equals to a, and this is basically f of x at the point a minus f of x at the point b, f of x at the point b minus f of x at the point a. So again, if I know the distribution function, I will be able to find out this kind of probabilities for any values of a and b such that a is less than b. Okay, let us consider the next case. Suppose now a is also closed. So if a is closed, again I can write it as probability x is less than equals to b minus probability that x is strictly less than a. Now note that here I have x is strictly less than a. The idea is again the same, that well, if I try to find out both sides close, then that I can write as all the points below B, including B, and all the points below A but excluding A. So that's why it is in this form, and this quantity is same as distribution function at the point B, and this quantity is same as the left hand limit at the point A. That we have just pointed out here. Okay, let us talk about probability that suppose A is less than equals to X less than B. Again, I can write it probability X is less than B minus probability that X is less than A. So now I have I have B minus f of X, A minus. And the last possibility is that A is close, and which possibility we have not considered? We considered A open and B open we did not consider. Okay, A open, B open we did not consider. So now A open, B open, in this case it is probability X is strictly less than B minus probability X is less than equals to A. So it is left limit at B minus f of X at the point A. So different kind of probabilities that X belongs to different kind of interval, those things we can able to find out if we know the distribution function of a random variable. Okay, so with that I stop in this lecture. In the next lecture we will learn discrete random variable.